Okay, so we can deal now. We have enough tools and practice to deal with pure and mixed states. What are they? What the heck are they? Okay, pure states. Okay, we can call pure states simply by what we're calling a state vector. It's just a vector. And this represents sometimes just an object, just one system, right? It's just one system, or just one object. Okay, a spin, just one electron. Um, Sometimes represent one. If you're talking about quantum computation, you're gonna say one of the enclosed superconductor circuits. Okay, so it's just one, and they usually have one state. They do not vary within themselves. They are homogeneous. What I mean by homogeneous, they are in just one state. Okay, so I can just represent this as we said. Um, I could just represent as Cn. Okay, right. This is not bad. We talked about two different properties of the density matrix. First, there was the square of it is itself, and that the trace of it's just one. Correct. And you can see this. If this is simply normalized. So if all this together are gonna make one, and therefore the dynamic matrix should make one. You have itself, or if you have a state that has basically the same, is basically itself, where it's basically a psi again, you're gonna have a probability of one of being that state, of course, because you already are in that state. That's trivial. So, okay. So with those two, we can say the trace of the density matrix squared is 1. This is useful for us later on. Okay? And what I mean later on when we compare it to mixed states. Okay? What are mixed states? Mixed states, as I said to you, imagine a cloud. I have states that are not the same states. They're made of multiple objects. Made of multiple objects. Okay? Same as saying made of more than one system. They're not all in one state. You cannot represent by a pure state. They're not all homogeneous. They're not all in the same state. Okay, if they were in the same state, you could well represent by a density matrix. That's fine, as we did above. But there's no need in that. However, if they're different, each object is different in different states, then you need to use the density matrix. And that's basically what we said. We have different parts of our cloud of objects, our set of objects with different states and different densities at each part of the cloud of the set of objects. Okay. Okay. So let's allow our I want to call it cloud to have an object. An object, okay? Such that Ni is the number of objects in psi I, in a specific state psi I, okay? And that's a pure state. And we can assert that the sum of n is equal to n, right? Because it's a sum. This is a sum for a specific specific state. The total number is just going to be the total number of objects. Okay. Okay. The probability of finding any object in state psi I is, denote this pi, which is ni divided by n, okay? Because what's the probability of finding 5 bananas and 10 fruits? It's gonna be 50%, okay? And we can see pi as we defined, but we sum it up. Sorry. Okay, that's how as we defined. Okay. So we can write rho mixed, which is the probability density of the mixed cloud, right, as a weighted sum. Okay. What is weighted sum? We're gonna have rho mixed equals pi. So the probability, so this is the probability of finding any, there's a probability of finding any specific vector or specific object in the state, and this is the probability matrix that by definition this is rho I, okay? And we sum it up, we got mixed. Just a weighted sum. Okay. Now, what if we do mixed squared? We have to do a double sum pi, pj, okay? So it's basically just saying that I'm squaring it, but I need to square and multiply by every single component, right? I need to just distribute it. So I need to multiply by every single component. Okay, so okay, this is done. Okay, now this can be used to find a trace. We're gonna see why right now why I want to find a trace. I've mixed, right? Mixed. So I'm basically just using the definition that we built up to this point. Okay. I, J, P, I, P, J. Okay, we're just copying from above. Okay, looks messy. Sorry, I forgot N here to close it up. Just using definition. Also using what we wrote in here. Okay. What can we simplify? Well, we can bring this in. We can bring this in. So we just have I, J, J, P, I, P, J. Oops. And what is this? Then a matrix again. So we can just cross it off, right? And in the end, we have I, J, P, I, P, J. J, J, I. Just let it not be too messy. Okay. Now, dot product is commutative, right? You can just commutate this, and you basically get just is squared. Right? We can clearly see that this is greater than just simply this, right? Not lesser, right? Because if I have probability, imagine I have probability of 2, I time it again with 2, one half, sorry, not 1/2, 1/2, I get 1/4. So this is less. This is gonna be always less than just simply this. And what is this? Right? What is this? This is simply just a one state. And we can see right here that if one pure state, we have the trace of squared being 1. So this is always this is 1, right? This is going to be 1, as we wrote above. This is just the trace squared for pure. So it's going to be 1. Okay, so it's always going to be less than 1. But how can we use it? We see that the trace probability squared is always going to be for a mixed state, it's always going to be less than 1. And if you want to maximize or achieve maximally mixed, so if I want to achieve total randomness here, I just want to like find the most I can do it. I have to have this condition where D is the dimension. So I have something that has only 2 dimensions. The max I can have here is 1/2. The max I can have that, right? Because because I can only have a mix, right? If I only have 2 states, you have 2 states, 2 basis states, right? And basically here, if we consider this as being 2 bases, we can call this a Kronov product for those who know what that is. And this is just gonna simplify to then pi squared. Okay, and we see clearly that this is gotta be bigger than this. Okay, so if we have only 2 possible states to be in, and there are 2 orthogonal states, then I can only have a mix of them 2 being mixed together, right? And how can I achieve even mixedness, as I would call? Just having half in one state and half in the other. And that's basically what we got here, 1/2, right? Well, what about if you have 3 states? Max, I can have 1/3. Why? Because I have each state, let's say each state is even distributed, so I can have maximum mixed. I don't have one that it's overpowering the other. Then I have always this, right? Always have this rule. So we can use this to determine how my whole cloud or mix is scrambled, or how mixed it is. Okay, how mixed it is. Okay, this is actually useful. This is actually useful if you have, I don't know, you have a quantum system for, I don't know, your computation, or you have something that has multiple spins, nuclear spins, electron spins, whatever. You can see how it evolves in time, or how we achieve this, and what is want to go to. Usually systems want to go to a even mix, right? But if they're not, there must be a mechanism there that is stopping them from going there. Okay, if I don't have a mix, that means that there's something stopping it from going to the mix. And then you can study whole systems of quantum information. You can the whole systems of molecules, of a single molecule, or whatever. Okay. This follows a lot of stuff. Hand's rule, that we have 1 up, 1 down. It's because you want to distribute in that way. You want to cancel it out. You want to go to the lesser energy state, right? You want to go to somewhere that it's um, less for energy than having one overpowering the other, right? Because if I have two orthogonal states, they're gonna have opposite energies. They're gonna cancel out to zero. Okay, so I'm gonna show one application of this. All right, one application of this is what we call NV centers. Okay, NV centers. I recently learned this in a class. They're basically vacancy, nitrogen vacancy centers in diamond. So you have a lattice, and one molecule is, you have a nitrogen here, and you have your carbon here, you have your 3 carbon here, your other carbons here, right? But this is a vacancy, it's missing an atom here. So you get this, but it acts like you're missing atom, but it acts like an atom. It still can you present it as an atom, which is incredible. So this is why it's called vacancy. And this will actually give colors to diamonds. But you have multiple electrons here because of covalent bonds, and the other atoms give electrons to them. So, but there you don't have your interaction with other, you're not orbiting, you're specifically confined to that vacancy center, right? So you can make operations in that vacancy center because you always have one extra electron. Okay, you always have one extra electron. I could explain why, but it gets more complicated where it comes from. I want to keep this brief, okay? But in the end, if I have multiple vacancy centers, I could measure it. How we measure vacancy centers is through light. So it's photoluminescence, how much light is given to us. And that is because you have transition states, right? And different sites have different transition states, right? Different states, right? Right. So we have actually one in truth, this is excited. Both can be excited. 0 and 1. It's not as if one is excited and the other one's less excited. Both is excited. It's just one gives off more energy than the other one. Okay. So one gives more energy than the other one. For example, this is 1. The other one gives more energy. Okay. So since one gives more energy or gives a higher wavelength, have one photoluminescence being higher than the other. Okay. But then I have something called decoherence. What is happening is that fluctuations in my environment gives energy out. Okay, gives energy out. So I lose energy, and when you lose energy, you flip you change your state. Okay, but in a diamond, I have multiple of these vacancy centers. I have multiple. Okay, they're multiple, but each of them have, it can be represented by one specific state, one pure state. But together, what they will make, as I said, a mixed state. And we call this this energy This is the T1 time, decoherence time, to exchange energy to surroundings. Okay, you're exchanging your energy to surroundings. What will happen? Some of them will become 0. Some of them will be 0 actually, and will become 1. So let's give an example. We start all at 1, okay? And what we're gonna see? A decay. Decay of the whole mix system, the whole cloud or the whole diamond going to, what is this? This is our mixed. And what is this? This is half. This is half of them. And as I said, this is just 2-dimensional. This is just this. Okay? This is 2-dimensional. So I'm going to have a probability of each one having 1/2. And there's no way I can represent just one specific one as a pure state, because there are multiple of them. There are multiple envy centers where each one is going to be a specific state. So over time, okay, this is time. So what happens here is that I initialize the state, I measure after tau, tau naught, and then I do it again. I reinitialize and I measure after tau 1, and I repeat this. Okay. Okay. So I repeat this, and I have this curve, which is usually represented by an exponential decay. So we can see that if there was something that was stopping this from going to or asymptotically approaching this density matrix, this maximally mixed density matrix, there's something to stop it, right? There was something in there. That's how we determine those things. And this is very useful for us to study experimentally things and how to represent whole systems of quantum states. Okay. So all right. So this is it. A lot of stuff, but we can do a lot of stuff with this idea of density matrix. All right. It's not as if I could just represent as vectors. I need some way of representing probability, which is basically what quantum is. Okay. All right. See you guys later.